At the far boundary where the solar wind thins into the broad hush of interstellar space, a faint point begins to drift into the reach of long exposure surveys. Arrays designed for routine cataloging catch it first. They classify everything by motion, color, and brightness, and at this great distance it is nothing more than a small fast streak crossing a field of scattered stars. The detection systems pass it along to the standard clearinghouses that feed thousands of nightly reports into shared tables. Its values slide naturally into columns that handle expected uncertainties, and so the object enters human awareness without any urgency or unusual annotation. Its provisional record is clean and almost unremarkable. Yet, in the same early hours that the first entries appear, a set of separated observatory clocks drop a second from their internal logs. The missing interval is small and known to happen occasionally during software updates, yet no update is scheduled. The event folds into routine diagnostics, but the absence lingers in the system's text summaries as if it is part of the same quiet arrival. The object's motion through the outer heliosphere continues without spectacle. Its brightness oscillates within normal margins for distant, icy material heated by the first touch of sunlight. At this stage, astrophysical expectations remain simple. Interstellar fragments sometimes pass into the gravitational domain of the star, and most leave again unchanged. Nothing about this visitor is yet known to be different, and the velocities and angles derived from its earliest positions align with that quiet tradition. It appears to be one more piece of material drifting between stars, carrying its long history sealed within layers that instruments cannot yet resolve. Observers who review the entries note only that its speed is high, even for a visitor of this class, though high speeds are themselves part of the reason such objects reach these regions at all. Global networks share the information automatically. Software harmonizes measurements taken under different atmospheric conditions, different exposure times, and different calibration states. In this process, images and tables from many continents begin to form a trajectory that reveals the first reliable signs of its approach. Observers refine the position angle by comparing each night's updated values with the previous line in the evolving ephemeris. The object's path through the outer system appears clean with no marked deviation that would challenge the early calculations. Navigation teams assigned to keep the solar system's inventory accurate mark it as interesting but still typical. Yet the missing second continues to behave oddly. It appears not in a single facility but in a small scatter of stations that use different timing hardware. Some maintain atomic clocks in temperature-controlled vaults. Others rely on stable microwave references tied to long baseline radio networks. Though the timekeeping systems differ, the skip occurs at precisely the same coordinate moment when traced back through their logs. The subtlety prevents immediate classification as a genuine anomaly because timing alignment often involves complex chains of intermediate signals. Still, it refuses to average away in the subsequent data reduction. It holds its own space in the records, as if part of a border phenomenon that remains obscured by distance and the scarcity of new observations. More nights pass. As the object continues inward, its brightness grows at a steady rate that indicates the activation of surface volatiles. This is common among comet-like bodies warmed by sunlight after long periods in cold interstellar regions. Gas escapes slowly at first, carrying dust that broadens into a faint envelope around the nucleus. The coma is small, nearly point-like, and reveals little about the underlying composition. The object remains too distant for rich spectral detail, though its trend suggests reflective ices with a thin scattering of darker grains. These readings match many typical interstellar conjectures, and no instrument yet reports anything beyond the expected patterns. Tracking centers in several countries revise their orbit solutions as survey telescopes collect longer arcs. Each line of input narrows the predicted path, reducing uncertainties in velocity and direction. Observatories coordinate follow-up slots to watch the increasingly accessible region where the object is expected next. This distributed choreography is familiar within the global detection community. The same procedures have guided the mapping of countless small bodies, and once again the systems respond with smooth updates. Despite the object's high speed, the calculations become more precise and its future location becomes easier to anticipate. A quiet sense of scale begins to form. Any interstellar visitor brings with it the reminder that the solar system is not closed. Each arrival opens a narrow window through which another region of the galaxy touches this one. The boundary between environments is soft, defined by field lines and flows rather than by walls. As the object moves farther into the heliosphere, its material and its trajectory become shaped by those structures. Solar radiation begins to warm its surface. Solar magnetism begins to alter the plasma in its growing tail. Its presence is no longer purely interstellar. It becomes a participant in the local dynamics, even if only for a short time. During this early stage, a separate set of instruments records slight irregularities in background light patterns. Wide field arrays that monitor the outer sky for transient events register a handful of near simultaneous brightenings at distances too great for tightly correlated astrophysical causes. Analysts note the coincidence but remain cautious because such fluctuations often arise from subtle calibration drift or seasonal changes in scattered light. Still, the timestamps of the brightenings align with the first few points of the object's inward trajectory. They may be unrelated, or they may signal some form of common influence carried through the shared medium. As the object approaches the region where sunlight strengthens noticeably, interest grows among both professional astronomers and experienced amateurs. The event begins to attract coordinated attention not because there is yet anything unusual, but because interstellar visitors carry a kind of natural importance. They represent conditions shaped outside the solar system, traveling for unknown spans of time before brushing the domain of human observation. Researchers hope for closer looks that will reveal composition, activity, and structure. For now, the object remains distant, a brightening point moving inward with a predictable grace that matches the early calculations. The missing second remains in the logs. Each new line of observation drawn from the global network settles the object more firmly into the shared tables used to trace thousands of bodies through the sky. Facilities that differ in aperture latitude and purpose contribute to the expanding arc of measurements. Data from large survey arrays merge with precise astrometric frames from smaller dedicated observatories. In this combined stream, the object's path begins to acquire definition, folding gradually into the stable frameworks that the solar system's watchers have refined for decades. These frameworks take the diffuse sweep of raw images and turn them into clean numbers that move steadily from uncertainty toward clarity. Every orbit, every trajectory becomes real through the patient repetition of this process. The object's entries behave well at first. Predictive ephemerides match the subsequent measurements closely enough that analysts trust their early models. A small and steady brightening curve supports the assumption that familiar volatile ices have begun to activate under increasing sunlight. From these initial patterns, the global coordination teams prepare for the next stage, tracking it across the transition from the outer to the middle heliosphere. This transition often reveals differences between ordinary comets, dormant fragments, and more exotic interstellar remnants. Yet nothing about the visitor forces any revision. The values fall into place as though built for these tables. But timing discrepancies return in subtle, persistent ways. When the minor planet center aggregates incoming data, the timestamps resist clean alignment. Observatories often differ by a fraction of a second in their reports, and standard practice allows for tiny offsets due to atmospheric delay, camera readout, or data transfer. Here, though, the offsets develop a curious consistency. The same handful of institutions located on different continents and using different timing hardware submit records that drift together by exactly the same amount relative to the others. The drift remains small but refuses to scatter randomly. At first, analysts flag these entries as probable calibration issues. They add notes reminding observers to verify their systems, but the verification reports return clean. The instruments are functioning normally. Further analysis sweeps these discrepancies into broader timekeeping checks. International centers compare clock networks that govern everything from radio telescope interferometry to satellite synchronization. Cross-correlation tables show that during windows when the object is observed, a shallow deviation forms across several systems at once. The modification is too small to affect most operations and would have remained entirely unnoticed if not for the deep precision of astrometric work. Yet it remains visible, a gentle shift that nudges the shared timekeeping grid by the same directional amount whenever the object's light curve enters a night schedule. For most analysts, this is still an operational puzzle rather than a physical phenomenon. Timekeeping is complex, nested in layers of correction that involve local oscillators, global reference signals, atmospheric models, and digital protocols. A misalignment can propagate through such systems silently. The prevailing explanation is simply that something transient in the infrastructure is creating a synchronized distortion across multiple networks. It is unusual but not unthinkable. The question is why it correlates so neatly with the nights when the object is tracked. No mechanism is proposed because none is yet needed. The teams simply continue to watch both the sky and the clocks. As the orbit calculations improve, astronomers assign the object an informal name. The choice travels quickly through message boards, observatory status pages, and internal mailing lists. The name Atlas settles around it with the ease of something inevitable, though it carries no official weight. With a name, the visitor acquires a character within the community, and discussions refer to it in conversational shorthand, as though it has already taken its place among the catalogued wanderers of the system. Software packages begin to incorporate its designation, updating trajectory overlays and predicting future positions with increasing confidence. The naming sparks a modest surge in participation. Amateur astronomers with high-quality backyard equipment coordinate with professionals to extend the nightly coverage into more diverse conditions. Because the object moves rapidly relative to background stars, it rewards observers who can track its motion with high cadence. The worldwide distribution of these volunteers fills many temporal gaps that professional facilities cannot cover. The combined data set starts to show a faint but persistent flicker in brightness. This flicker mirrors itself across data sets separated by thousands of kilometers. What brightens in one hemisphere brightens in the other at nearly the same coordinate instant, even when weather delays one of the observations. The readings occur at different local times, but merge into a single coherent pattern when traced back to the shared temporal baseline. At this stage, the flicker remains small enough that it might be attributed to thin clouds, minor tracking error, or background noise. Yet those explanations require the noise to occur with coordinated timing across unrelated observatories. Analysts hesitate to declare a genuine correlation, aware of how easily artifacts can arise from reduction pipelines that share similar assumptions. They compare raw files, independent calibrations, and cross-instrument corrections. The brighter nights, when many observatories capture the object simultaneously, show the same synchronized rise and fall in counts. The dimmer nights occasionally fail to detect the pattern, but when the pattern appears, it appears everywhere at once. Orbital refinement continues. The speed confirms Atlas as the swiftest recorded visitor of its type, yet its path remains reassuringly stable. Deep space tracking systems, including those monitoring spacecraft that skim the inner regions of the heliosphere, integrate the object's influence into their broader dynamical models. Nothing external appears to disrupt its course. No planetary encounter comes close enough to demand unusual corrections. The gravity of the star, the pressure of sunlight, and the slow, predictable drag of outgassing together define a motion that fits within established expectations. Through all these quiet updates, the timing offsets persist. Countless factors can disturb the coordination of timekeeping systems, but the consistency of these disturbances suggests influence rather than accident. Still, observers refrain from premature interpretation. They simply note that the idea of folding the sky into tables, of translating a moving point into the polished clarity of orbital elements, now requires absorbing not just light and position, but an unnoticed collective irregularity in how the world keeps time. Something begins to press gently against the routines of measurement, not enough to force recognition, only enough to remain present until the next line of observation arrives. With the name Atlas now woven into nightly status reports, the visitor begins to live not only in the sky but in the routines of those who follow it. Observers in small domes on quiet hillsides check its predicted position before dusk. Operators at major facilities slip its coordinates into queue schedulers that must balance many competing programs. The object does not demand attention. Instead, it accumulates it minute by minute, exposure by exposure, until its path becomes one of the most thoroughly logged interstellar passages in the archives. Coordinated campaigns form around it, almost without comment. The planetary defense offices that normally concern themselves with potential impacts add Atlas to their watch lists, not because it poses any direct risk, but because tracking fast visitors refines algorithms needed for more urgent targets. The International Asteroid Warning Network circulates bulletins that standardize reporting formats and reference frames. This ensures that every observatory, from small university instruments to national facilities, can feed consistent entries into the global pool. The light curve produced from this effort takes shape gradually. Each datum is a small local measurement shaped by weather instrument response and human decisions. When combined, these scattered points reveal a smooth rise in overall brightness, shaped by the geometry of the orbit and the warming influence of the sun. The curve's general form matches what is expected of an icy body that begins to sublimate and shed dust as it approaches the inner regions. Yet superimposed upon this broad trend is a fine pattern that resists smoothing. Short, shallow rises and dips appear at times that are not easily linked to rotation alone, or to viewing angle, forming a rhythm that holds to no obvious mechanical explanation. This pattern would remain a curiosity were it not for its geographic coherence. Observatories separated by oceans operated under different funding agencies, and using distinct data reduction pipelines, submit measurements that trace the same small excursions in brightness. When plotted on a shared temporal axis, their points rise and fall together with a precision that outpaces the likely coordination of clouds seeing conditions or human error. Analysts test this impression by shuffling timestamps, by introducing artificial delays, and by comparing nights when Atlas is not in view. Only when the object is present do the synchronous excursions emerge. On other nights, the same instruments report uncorrelated noise that scatters in the expected way. The community does not rush to declare a new phenomenon. Instead, discussions unfold in quiet channels, in internal memoranda and after-hours conversations. Some propose that a subtle calibration standard shared among several major surveys might be responsible, perhaps one that aligns their sensitivity curves in a way that inadvertently imprints common artifacts on the data. Others suggest that a global shift in atmospheric transparency, driven by upper-level circulation patterns, could modulate ground-based light curves across continents. The idea arises that the pattern may originate not in any single observatory, but in something that all are sampling together. To test this, analysts isolate events where the object's brightness changes sharply over a short interval. These intervals become markers for what are later called simultaneous light anomalies. In them, the measured flux jumps or dips at the same coordinate time across multiple facilities. The magnitude of each anomaly is small, easily hidden within broader variability, yet the temporal alignment is striking. It does not respect local night boundaries, operational schedules, or data transfer latencies. It respects only the shared time standard that underlies all reporting, the coordinate grid that allows hands-on distant clocks to point to the same unseen moment. Amid these developments, the object itself continues to behave in ways that appear broadly comet-like. Its coma thickens as gas and dust flow off the surface. The tail extends along the expected curve away from the sun, tracing the integrated effects of radiation pressure and the solar wind. Spectra begin to show familiar lines from water and simple carbon-bearing molecules mixed with more complex signatures that are harder to disentangle at the available resolution. In this sense, Atlas behaves like a bridge between the known and the new. It provides comfort to models that rely on standard comet physics, while also carrying patterns that do not fit neatly into those templates. Over weeks, the simultaneous light anomalies trace a faint structure through the calendar. They occur neither randomly nor with simple regularity. Instead, they follow the object's trajectory in a way that suggests an interplay between its changing distance, its growing activity, and the invisible geometry of the surrounding fields. They are strongest when Atlas passes through certain configurations relative to the Sun and the broader heliospheric environment, and weaker in others, yet they never vanish completely. The result is an impression that the visitor is not only reflecting sunlight, not only shedding gas and dust, but also participating in a more diffuse pattern that links instruments and observers into a shared delicate rhythm. In this way, Atlas's name takes on a second meaning. It no longer refers only to an object with a path and a nucleus. It begins to denote the complex map of interconnections that arise around it, observatories, networks, clocks, archives, and the fine thread of anomalies that tie them together. The Atlas is not only on the sky, but within the infrastructures that watch the sky, a slowly unfolding chart of how a single visitor can touch the global apparatus of measurement while still following an apparently ordinary course. As Atlas sweeps farther inward, its speed becomes a quiet refrain in every briefing. Compared with the long catalog of local comets and asteroids, this visitor moves with a decisiveness that stands out even to those accustomed to fast trajectories. Orbital solutions describe a body that crosses the space between the outer planets and the inner system in a fraction of the time taken by most long-period comets. The language in those solutions stays dry and precise, yet behind the figures lies the sense of an object that has carried its momentum across interstellar distances and now threads the solar system in a single continuous passage. Despite this high speed, the trajectory reconstructions remain calm. Each new observation refines the orbital fit rather than disturbing it. Even when alternative models are tested, allowing for a generous range of non-gravitational forces, the best solutions cluster tightly around a single family of paths. This is unusual for an active body moving so quickly. Outgassing jets can act like small thrusters, introducing accelerations that push a comet away from a simple gravitational arc. Many known objects require complex adjustments as their surfaces turn and their activity flickers. Atlas appears to avoid such complexity. It responds to sunlight by brightening and shedding material, yet the resulting thrust never grows strong enough to create dramatic deviations. Specialists in celestial mechanics test this impression with care. They reconstruct the orbit using straightforward position fitting, then repeat the work with dynamical models that incorporate solar radiation gas jets and the faint drag from heliospheric plasma. In each case, the residuals, the small differences between predicted and observed positions, shrink as the data arc lengthens. Instead of wandering, the path tightens within the models, as though the object prefers a particular compromise between all the forces that touch it. The fastest visitor becomes, in a sense, also one of the most cooperative. Independent groups repeat the calculations with their own software and assumptions, sometimes excluding entire blocks of data to test whether hidden biases might be shaping the fit. The results scarcely change. Whether the orbit is built from professional surveys alone or from a blend that includes carefully vetted amateur measurements, the same quiet pattern emerges. Atlas races inward, yet its non-gravitational terms remain smaller than early fears suggested, as though the object is content to accept the path that gravity and gentle fields together have prepared for it. Yet the residuals do not vanish. When plotted against time and heliographic longitude, they sketch a faint pattern that does not align neatly with the direction of sunlight. In many active comets, non-gravitational accelerations point roughly away from the star, reflecting the combined push of gas and dust rushing from the surface. For Atlas, the tiny departures from a purely gravitational track show a different bias. They curve gently along structures that resemble the geometry of the heliospheric magnetic field. Where the large-scale field bends, the residuals bend with it. Where the field intersects the warped sheet that divides opposite polarities, the residuals show small inflections that repeat over several turns of the star. Analysts compare the timing of these deviations with maps of the heliospheric current sheet produced by solar observatories and space weather models. The match is not exact, the field is complex and constantly reshaped. Nevertheless, the alignment is persistent enough that it resists easy dismissal. During passages when Atlas is predicted to cross regions of strong magnetic curvature, the residuals tend to point in directions that suggest a coupling between its extended atmosphere of gas and plasma and the surrounding field. The effect is subtle, far too weak to pose any hazard, yet strong enough to leave a measurable trace in the shared tables. In this view, Atlas behaves like a seed of ionized matter carried along not only by gravity and the pressure of light, but also by the larger-scale magnetic topology of the star. Its substantial speed amplifies the effect. Because it crosses great distances in relatively short intervals, small continuous influences accumulate into patterns that instruments can detect. The fast passage turns the heliospheric environment into a three-dimensional map, etched into its trajectory, revealing gradients and boundaries that would be harder to read from slower, more erratic travelers. Even so, the prevailing tone remains quiet. The object is fast, but not beyond comprehension. Its non-gravitational accelerations are present, but small. Its apparent coupling to the magnetic environment is intriguing, but sits near the limits of measurement. The aim is not to grant intention to its motion, only to recognize that even a fragment from deep interstellar space cannot pass through the complex fabric of the heliosphere without reflecting its patterns. Atlas becomes a case study in how those patterns express themselves when a body arrives with a particular combination of composition, speed, and orientation. As it continues inward, the balance between routine tracking and emerging curiosity settles into a steady rhythm. Each new observation strengthens the picture of a visitor that is both extreme and restrained. It moves faster than any previously cataloged comet-like body, yet shows fewer erratic deviations than many slower, more familiar objects. The fastest visitor carries a quiet trajectory, one that aligns not only with gravity's pull, but also with the deep, slowly changing lines of force that thread the space between the planets. Within this balance, the solar system's monitoring networks learn to read their own environment, more finely guided by a fragment of matter that has traveled far to write a thin, precise path into the surrounding fields. As Atlas draws nearer to the inner warmth of the star, attention shifts from simple brightness counts to the quieter language of heat. Infrared observatories in Earth orbit and deep space turn their detectors toward the visitor, adding new bands of information to the archive. Where optical images trace reflected light and scattered dust, thermal measurements show how energy sinks into the object and flows back out again. For bodies coated in familiar ices and dust, sunlit regions brighten in the infrared shaded regions cool, and the contrast between them depends on how quickly the surface conducts and radiates heat away. Early thermal snapshots of Atlas appear to follow this template. Its warmer side faces the star, its cooler side trails in shadow, and the overall emission roughly matches what is expected for a small icy nucleus. Yet even in these first maps made while the object is still comparatively distant, analysts notice departures from expectation. Certain zones that should be among the hottest remain muted. Other regions that should remain relatively cool show a persistent warmth, as though energy lingers there longer than the models allow. To probe this, teams combine datasets from different platforms. Spacecraft monitoring the inner heliosphere contribute coverage when ground-based facilities are in daylight. Earth-orbiting observatories provide higher resolution when conditions permit. Together, these vantage points build composite maps that follow Atlas as it spins and travels, tracking which parts of its surface see the star at any given time and how the emitted heat responds. The composites reveal that the surface does not behave as a simple passive shell. Warmth seems to migrate in patterns that are not fully explained by rotation or by changes in the angle of sunlight. Some sectors warm early before sunrise reaches them by ordinary geometric reckoning, as though heat from elsewhere is redistributed along unseen channels beneath the surface. Other sectors cool later than expected, holding on to thermal energy after long intervals in shadow. The resulting distribution looks less like a smooth gradient between day and night, and more like a shifting mosaic of patches that brighten and fade according to a slower, more global rhythm. Researchers adjust the models. They vary surface texture, with some regions more insulating and others more conductive. They add plausible subsurface cavities and fractures through which gas might circulate and carry heat. Many such combinations succeed partially, but none resolves all the discrepancies. In every case, residual patches remain zones that either refuse to warm fully or refuse to cool, no matter how the virtual surface is rearranged. A different pattern emerges when the thermal maps are folded against time rather than shape. When analysts line up snapshots taken at different rotational phases, but at similar distances from the star, and plot them on the same coordinate timeline used for brightness and timing studies, a soft pulsing becomes visible. The entire thermal field appears to breathe in slow intervals, brightening and dimming together by a small but measurable amount. This rhythm shares key moments with the simultaneous light anomalies already charted. Small surges in overall thermal emission tend to cluster near the coordinate times when brightness from Atlas jumps across the network of telescopes. Thermal responses lag optical changes by the intervals associated with heating and cooling, yet the alignment remains close enough to suggest a single underlying cadence. Light and heat, sampled by different instruments and processing chains, appear to respond together to a slow modulation that is not solely set by rotation or by changing distance. The realization spreads quietly through teams working on separate parts of the problem. Groups focused on radiative transfer compare notes with those tracking non-gravitational accelerations and timing offsets. Magnetospheric specialists examine whether the thermal pulses align with predicted crossings of the heliospheric current sheet or with structural features in the solar magnetic field. Some correlations appear promising, though the mapping between models and the path remains uncertain. Instruments themselves come under scrutiny. Infrared detectors are prone to drift, and the pipelines that process their data include layers of correction designed to remove spurious trends. Analysts revisit calibration logs and comparison fields and look for seasonal changes and hardware aging. Parallel observations of other objects in similar parts of the sky taken with the same instruments in the same intervals do not show matching pulses. The effect appears to be specific to Atlas. As more data accumulate, the term thermal divergence begins to appear in internal documents. It refers not to any instability, but to the persistent way in which Atlas's heat maps refuse to converge to a single simple solution. The divergence is between expectation and observation, between the behavior of a surface that should be governed by local illumination and conduction and the behavior of one that seems to follow a global pattern. Atlas is still described in the formal terms reserved for comet-like bodies, yet the descriptions now include the acknowledgement that its warmth behaves as if guided by a timing pattern threaded through the broader network of measurements. In the combined view, Atlas is no longer only a fast visitor with a stable orbit and a distinctive light curve. It is also a moving patch of thermal behavior that pulses in quiet synchrony with brightness anomalies and subtle timing shifts. Heat, light, and time begin to form a single tapestry of evidence hinting that the object's relationship with the surrounding environment involves more than simple reflection and outgassing. It behaves as though some gentle, coordinated process is adjusting how and where energy is stored and released on its surface, in step with a rhythm that instruments across the system are just beginning to trace. As Atlas moves into the inner solar system, it enters a region where the familiar language of comets becomes easier to read. The thinning point of light has grown into a distinct head wrapped in a diffuse coma, and from this head a tail stretches away from the star in a pale sweep. Wide-field images from ground-based telescopes show the classic asymmetry that comes when sunlight presses on dust and gas, pushing material into a long plume. At first glance, Atlas appears to be what many expected all along, an active interstellar comet responding to the star in a way that fits established pictures. Closer inspection reveals a more layered scene. Embedded within the broad tail are finer structures, narrow streams, and jets that branch from the coma at specific angles. Long exposure images from amateurs and professionals show these features as ghostly lines that change from night to night but retain a recognizable pattern. A main tail sweeps back along the direction of orbital motion. Additional jets fan outward, some aligned with the direction away from the star, others curving along paths that are not easily explained by simple radiation pressure. Near the inner core of the coma, where the unresolved nucleus hides, bright knots pulse and fade in ways that suggest localized sources on the rotating surface. Spectroscopic observations tie these structures to distinct components of the material escaping from Atlas. Dust-rich jets appear brighter in reflected sunlight. Gas-rich jets glow in lines characteristic of specific molecules and ions. Some streams show enhanced signatures of charged particles, indicating that they are tightly coupled to the solar wind and the magnetic field that threads through it. By separating these contributions, researchers see that Atlas hosts not a single tail, but a layered system: dust, neutral gas, and plasma, each responding differently to the star and to the surrounding heliospheric environment. As the orbit intersects regions where models predict crossings of the heliospheric current sheet, the sheet that separates opposite magnetic polarities, the behavior of these components becomes especially revealing. The sheet is not a flat plane, but a warped surface that rotates with the star. Where Atlas descends through this surface, instruments record changes that appear not only at the moment of crossing, but also in the hours leading up to it. Jets that had been faint begin to brighten before the predicted encounter with the boundary. The plasma-rich tail sharpens its structure and extends farther than expected, as though anticipating the change in magnetic orientation. This anticipatory quality is subtle but persistent. When analysts overlay the predicted current sheet crossings with time series of jet brightness and tail shape, they find that the most pronounced enhancements tend to begin slightly before the object reaches the modeled boundary. The lead time is modest, on the order of hours rather than days, but it recurs often enough to draw attention. It is as though the extended atmosphere and plasma environment around Atlas senses the approaching transition through gradual changes in field geometry and responds by reconfiguring itself before the crossing is complete. Spacecraft distributed through the inner system supply additional context. Solar wind monitors near the orbit of the homeworld, and farther out record shifts in magnetic orientation, particle density, and flow speed as the rotating structure of the heliosphere sweeps past them. By comparing these measurements with the times when ATLAS shows enhanced jet activity, researchers trace a pattern in which the visitor appears most reactive when it is embedded in regions of strong field curvature or near the boundary where polarity reverses. The effect is not binary. Rather, the comet-like system seems to slide through a gradient of conditions with its own plasma sheath adjusting in a way that sometimes precedes the modeled markers. Yet the link between these changes and the wider network of anomalies that has grown around ATLAS is difficult to ignore. When the comet-like body approaches a current sheet crossing and its jets brighten ahead of schedule, simultaneous light anomalies become more likely across the global telescope network. At the same time, subtle adjustments appear in timing systems and magnetometer arrays that have no direct connection to the observing facilities. Thermal divergence grows more pronounced, with heat maps showing distinctive rearrangements during and around these passages. The object, its tail, the heliospheric structure, and the planetary systems that watch them seem to share a loosely coordinated rhythm. In visual terms, composite images combine filters tuned to specific ions with broad exposures of dust and gas. The plasma tail streams out as a thin thread, sometimes bending at angles that reveal the invisible shape of the magnetic field. Dust traces a broader fan whose curve reflects the history of grains released over weeks. Jets nearer the coma show transient bursts that fade as they are carried away, leaving faint striations along the main tail. Over time, sequences of such images create a kind of moving diagram, a record of how the object's outer behavior encodes its passage through the electromagnetic landscape of the inner system. ATLAS therefore becomes an interpreter as much as a traveler. Its evolving coma and tail translate changing field conditions into patterns of light that instruments can capture. The anticipation seen in the jets hints that the translation does not wait for sharp boundaries but responds to gradual shifts in the medium. The comet-like appearance anchors the object within known categories, yet the timing and coherence of its responses keep open the possibility that something more systemic is unfolding, something that reaches beyond the surface of the visitor and into the wider fabric of the heliosphere and the planetary infrastructures watching it. As ATLAS rounds the inner bend of its path near the star geometry reshapes the way it can be seen. Before perihelion, most views come from the homeworld's night side, with the comet-like body standing against the distant background of stars. At closest approach to the star, that alignment breaks. The object moves into regions of the sky too near the solar glare for many ground-based telescopes to follow. Instead, instruments positioned far from the planet take the lead. Space-based observatories in solar orbit, probes near other worlds, and coronagraphs that stare constantly at the star all turn their attention to the visiting fragment from interstellar space. The Hubble Space Telescope captures images when angular separation allows brief windows of darkness around the object. Solar orbiters maintain almost continuous watch when ATLAS passes through their fields. A European orbiter around a neighboring planet adds still another vantage point, imaging the visitor as it moves against a different background of constellations. Together, these instruments form a three-dimensional net of observation around the inner system. Each has its own cadence, sensitivity, and field of view, yet all contribute measurements that tie back to the same reference timeline. From this wealth of perspectives, a new expression of the earlier brightness anomalies takes shape. During several key passages near perihelion, the object displays brief, sharp changes in light output that are recorded almost simultaneously by widely separated instruments. A solar orbiter sees the coma and tail brighten in a narrow band of wavelengths. A telescope near the home world records a matching rise in integrated brightness even through scattered light. The orbiter around the neighboring planet registers the same feature at nearly the same reported instant, despite the distance between worlds and the different paths that light must take to reach each detector. Under ordinary circumstances, analysts expect such events to align in emission time rather than in observation time. Light leaves the object, travels outward at a fixed speed, and arrives at each instrument at slightly different moments depending on distance and path. When these differences are corrected, the signals should converge on a single emission interval. For ATLAS, something more peculiar emerges. When time delays are removed, the brightening events do not compress into one neat spike in emission. Instead, they appear spread out as though the object brightens differently toward each observer. When delays are not removed, when analysts look simply at the raw coordinate times stamped onto the data streams, the peaks align more closely. This behavior becomes most evident during a sequence of events that occur as ATLAS crosses behind the star from the homeworld's point of view. Ground-based observatories cannot see it directly, but relay satellites in artful orbits, together with solar probes and planetary orbiters, maintain coverage from other angles. On a particular day, a solar probe catches a sudden enhancement in the plasma tail recorded in ultraviolet light and in charged particle counts. Within the same narrow interval of coordinate time, though separated by millions of kilometers, the planetary orbiter registers a matching brightening in optical exposures. A wide field space telescope near the homeworld's orbit, looking slightly off the glare, notes an uptick in the overall luminosity of the coma. The travel times of light to these instruments differ by dozens of seconds to several minutes. Correction schemes that account for these differences yield a complicated picture of emission with no single clean spike that explains all three signals. Yet when analysts retain the timestamps as the instruments themselves apply them, the events line up to within the precision of their clocks. The brightening appears to be simultaneous in observation, not in origin, as though the global system of detectors is participating in a shared coordinated adjustment. These are the simultaneous light anomalies in their most fully developed form. Earlier versions seen when Atlas was still farther from the star involved small changes in brightness recorded by ground-based telescopes alone. Now the phenomenon extends into a full heliocentric geometry. Observers circling different worlds and sharing only the common framework of the timekeeping grid see the same flare of behavior at the same recorded instant. It is not that light ignores distance, but that the entire measurement network becomes the space in which the anomaly is defined. The institutions that manage timing standards examine the logs with care. Each instrument relies on clocks derived from atomic references corrected by radio signals and shaped by software that enforces coordinated universal time. The possibility of a systematic offset is considered. Perhaps a configuration change occurred in the deep space communication networks or an update in the way delays are modeled in telemetry processing. Yet no such changes are found that coincide reliably with the anomalies. System tests run on calibration sources during the same intervals do not display matching peculiarities. The simultaneity seems linked to the presence of Atlas in the field of view. Within data centers, the anomalies are first treated as puzzles of metadata. Analysts wonder whether file headers have been misinterpreted, whether one set of timestamps refers to reception time while another refers to emission time, or whether compression and decompression steps have introduced unnoticed offsets. Cross-checking with raw downlink streams reduces these possibilities. The brightening signatures can be traced back to the earliest stages of processing in each pipeline where times are tied directly to the onboard clocks of the spacecraft. Those clocks themselves appear healthy and show no unusual resets or drifts during the events. From a physical standpoint, several tentative explanations are explored. One idea is that the coma and tail of Atlas might be responding not to local conditions alone, but to a wave or disturbance passing through the heliospheric medium, influencing the appearance of the object differently for each observer. Another is that the surrounding plasma environment coupled to the star's magnetic field might redistribute energy along field lines in a way that shapes the visible emission pattern. Yet each of these mechanisms would be expected to leave signatures in other nearby objects and background field signatures that are largely absent. In the absence of a single convincing explanation, the anomalies are cataloged rather than resolved. They are described as simultaneous in the sense that they respect coordinate time across the network of observers, not in the stronger sense of on-site emission. The distinction is important. It frames the phenomenon as something that involves the entire system of measurement, from clocks to communication links to data archives, just as much as it involves the comet-like body at their center. Atlas in this phase of its passage becomes less a point source and more a nodal point in a web of coordinated behavior that stretches from the surface of worlds to the edges of the inner heliosphere. The night that later becomes known in internal briefs as the synchronization event begins without ceremony. Observatories around the planet turn toward their scheduled targets. Some include Atlas in their sequences following updated ephemerides that carry the visitor away from its closest passage by the star. Others watch galaxies' variable stars or near-Earth asteroids. Deep space communication arrays track distant probes, beam commands outward, and listen for faint replies. Magnetometer stations both on the ground and in orbit continue their steady recording of the planet's own field and the solar wind that shapes it. Time flows as it always does in such networks shaped by atomic transitions, disciplined by radio standards, and folded into the quiet pulse of coordinated universal time. Near the middle of this extended night, a trivial-looking correction propagates through several of the systems that maintain the global time base. It is small a shift, measured in millionths of a second, and of a kind that occurs occasionally as part of normal maintenance. Each timing center constantly compares its best local clock with signals from other centers and from satellite constellations. Differences accumulate slowly and are trimmed away by algorithms that keep the network aligned. Ordinarily, these adjustments are staggered and modest, tailored to the unique behavior of each clock. On this night, a pattern emerges that is only noticeable when records are later assembled side by side. Across multiple institutions in different countries and under different administrations, the timing systems apply almost the same microsecond scale adjustment at nearly the same coordinate moment. In some logs, the change appears as a tiny step. In others, it manifests as a brief period of accelerated or slowed tick rates gently nudging the clocks into a new alignment. None of these changes is large enough to disrupt daily operations. They do not alter civil time or navigation solutions in a way that any human would perceive. They simply reconfigure the baseline against which high-precision measurements are made. At first, nothing remarkable is attributed to this coincidence. The teams that supervise the timing infrastructure are accustomed to managing many interacting influences, environmental effects, hardware aging, and the slow drift of reference oscillators. The idea that several centers might converge on a similar correction at the same moment is not initially seen as remarkable. The global time standard, after all, is designed to keep all clocks as close as possible. But as data from the night are assembled for other reasons, a more subtle consequence becomes visible. Astronomers processing observations of Atlas notice that positional residuals along its path shrink when the new timing adjustments are applied. The same images run through earlier versions of the time standard produce slightly larger discrepancies between predicted and observed positions. With the updated clocks, the orbit reconstruction tightens. Light curve features that once showed small mismatches in phase with other datasets now line up more cleanly. The effect is not limited to a single facility. It appears across several observatories that rely on different instruments but share the same underlying time service. Elsewhere, teams comparing magnetometer readings from widely separated ground stations find that their cross-correlations improve when the revised timestamps are used. Tiny ripples in the planet's field, previously blurred across the network, become more sharply defined. Pulses that align with changes in the solar wind as measured by upstream spacecraft now match those external signals more precisely. Deep space communication centers correlating incoming transmissions from distant probes with command histories note that round-trip light time calculations show a marginally better fit under the new standard. The pattern becomes more striking when analysts overlay these improvements with the predicted trajectory of Atlas for that night. The moment at which many clocks apply the coordinated microsecond shift falls within a window when the object transits a particular region of space relative to the planets and the star. The exact geometry is complex, involving angles between the visitor, the homeworld, other observing platforms, and the folds of the heliospheric current sheet. Still, the coincidence is clear enough to draw attention. The timekeeping grid tightens its alignment at the same coordinate moment when Atlas occupies a certain zone, and the tightening yields better fits not only for the visitor's behavior but also for other seemingly unrelated measurements. No shared human decision can be found that explains the synchronization. Each timing center follows its own protocols which draw on local assessments and relative comparisons. There is no single command that could have ordered them to adjust together. The algorithms used to reconcile clock differences were developed independently, tested under varied conditions, and deployed over many years. The best they are meant to do is converge slowly toward consensus. On this night, they appear to leap together. The possibility arises that the convergence is only apparent an artifact of how logs are later aligned or how corrections are reported. Investigators examine raw configuration files, hardware telemetry, and satellite broadcast histories. They test alternative interpretations of the timestamps, searching for an overlooked offset that could spread the adjustments out in time. Those efforts reduce some of the apparent simultaneity but do not eliminate it. A cluster remains a period during which more clocks than usual apply more similar corrections than usual in a narrower span than statistical models would favor. The term synchronization event emerges among those tasked with describing the incident without overstating it. It refers not to a single global action, but to an emergent pattern in which many semi-independent systems carry out nearly the same adjustment at nearly the same moment, with beneficial consequences for the coherence of the data. Atlas is not formally included in this definition, yet practically it is never far from the discussion, because the improvements it brings to the fit of the visitor's observations are among the most tangible signs that something noteworthy has happened. From a broader perspective, the event highlights how deeply interwoven the planetary measurement infrastructures have become. Observatories, magnetometers, communication arrays, and navigation systems all anchor themselves in a shared temporal framework. When that framework shifts, however slightly, the adjustment ripples outward into every analysis that depends on precise timing. Under usual circumstances, these ripples are simply corrections that bring order to noise. In this case, the correction appears to align with an external configuration involving a fast interstellar object and the heliospheric environment it traverses. Speculation remains cautious. No one claims that Atlas has altered time. The more modest suggestion is that the presence of the visitor moving through a particular arrangement of solar and planetary fields might have coincided with subtle changes in signal propagation or reference stability that encourage the clock network to agree on a better shared standard. Whether this is coincidence or part of a broader pattern is left open. The key fact is that for a brief interval, the entire system of measurement seems to have taken a small collective step, and that step made the sky, the fields, and the interstellar fragment threading them all fit together with unusually smooth precision. As the orbit of Atlas carries it deeper into the architecture of the heliosphere, attention turns steadily toward the planet's own magnetic environment. Magnetometer arrays dispersed across the surface along coastlines and polar research stations and aboard satellites have long been tasked with monitoring the slow, ceaseless motion of the planetary field. These instruments record pulses from lightning waves launched by solar wind disturbances and the faint signatures of interactions between charged particles and the upper atmosphere. Under ordinary circumstances, the data from these networks show the natural diversity of local conditions. Each station hears the field through its own ground conductivity, latitude, and weather, and while global patterns exist, the fine details rarely align with the precision of synchronized instruments. During the months surrounding Atlas's interior passage, this familiar diversity begins to narrow. When analysts compare the magnetometer data from widely separated sites, they discover a series of small coordinated motions. A faint oscillation appears that does not match the usual rhythms of the solar wind or the planet's rotation. The oscillation is weak, nearly drowned in the background fluctuations that accompany daily geomagnetic activity. But when the data sets are placed side by side, filtered through identical passbands, and aligned on the shared timeline refined by the synchronization event, the pattern becomes visible. Stations separated by tens of thousands of kilometers record ripples that rise and fall within the same broad intervals. The simplest explanation is that a mild geomagnetic impulse has touched the field everywhere at once. This sometimes happens when large-scale solar wind structures sweep across the magnetosphere, compressing it slightly and releasing built-up tension. Yet the timing does not match any such structures recorded by upstream spacecraft. The solar wind, as tracked by distant probes, remains calm during several of the correlated episodes. No sudden increase in density or velocity, no abrupt change in magnetic orientation appears that could have driven the observed ripples. Gradually, analysts recognize that the ripples align more closely with the predicted position of Atlas relative to the warped surface of the heliospheric current sheet. Whenever the visitor approaches a region of strong curvature in the large-scale magnetic field, not precisely at the modeled crossings, but in the approach and departure from those boundaries, the planetary magnetometers begin to show the faint coherent drift. The amplitude of the drift remains small and its mechanism remains obscure. But the repeated correspondence suggests that the planet's field is responding to a structure or process that Atlas encounters as it travels through the magnetic geometry of the inner system. Space-based magnetometers aboard orbiting probes add a further layer of detail. A satellite trailing the planet detects small shifts in the magnetic vector that match the ground-based patterns, though with slightly different timing, as though the ripple passes through the magnetosphere from the outer boundary inward. Another satellite on the planet's day side senses a complementary variation. When the data from these platforms are transformed into a common reference frame, a picture emerges of a subtle system-wide rearrangement of field lines occurring during specific stages of the visitor's transit. The variations do not resemble those produced by coronal mass ejections or high-speed solar wind streams. Instead, they are quieter, more distributed, lacking the sharp fronts that define typical space weather events. They appear not as pulses, but as gentle adjustments that settle into the field and dissolve again over the span of hours. The patterns are faint enough that they might have escaped notice entirely were it not for the increased attention given to the heliospheric context of Atlas's motion. In this context, the non-gravitational accelerations measured in the object's trajectory take on new significance. Those small deviations that curve along the shape of the heliospheric magnetic field become part of a broader interpretation. Atlas may be responding to the same subtle forces that ripple through the planetary environment. If its extended atmosphere of plasma couples to the field even weakly, then its motion would reflect the contours and transitions of the greater structure. The global magnetometer arrays, meanwhile, appear to sense those same transitions indirectly through the quiet reconfiguration of lines of force that define the planet's magnetic shield. As the orbit carries Atlas through regions of compressed field curvature, the ripples deepen very slightly. They still avoid the character of storms or substorms. There are no dramatic spikes, no sudden surges of current in the ionosphere, no auroras unexpectedly flaring where they should not. Everything remains within the bounds of gentle motion. But the coherence across stations strengthens the impression that the field is subtly tracking a passage not just of matter but of a changing electromagnetic context. Correlations with terrestrial timekeeping systems begin to emerge as well. When analysts overlay the magnetometer ripples with the timestamp adjustments from the synchronization event, and with subsequent micro-adjustments made quietly by the clock grid, they find that periods of enhanced magnetic coherence align with moments when the time standard improves its own internal consistency. The field and the clocks appear to shift toward a more ordered configuration at the same stages that the visitor interacts with certain heliospheric structures. Neither correlation is perfect, yet both recur often enough to suggest a repeating geometry rather than chance. Some begin to speak of magnetic threads, a metaphor for the faint lines of influence that seem to tie the object's transit, the planetary field, and the global timing system into a shared pattern. The phrase does not imply any particular mechanism. It simply provides a way to describe the subtle low-amplitude coherence that emerges wherever these data sets are viewed together. In this framing, Atlas is not altering the magnetic field. It is moving along paths shaped by the field, and the field responds in ways that instruments around the planet can detect. Across the archives, from ground-based magnetometer lines to deep space telemetry logs, a sense grows that the visitor's passage is revealing not only its own nature, but also the hidden structure of the heliospheric medium itself. Atlas becomes a tracer, a luminous seed carried through an immense invisible fabric of magnetic forces, and in its wake, instruments of many types register soft echoes of that journey. The coherence is quiet, almost shy, always retreating into noise when scrutiny grows too sharp. Yet it persists, hinting at a broader interconnected environment in which the visitor, the star, the planets, and their instruments all drift through shared lines of influence. Long before Atlas appears, the planet's digital archives already carry the marks of constant invisible repair. In data centers beneath cities on mountaintops and in remote deserts, storage arrays work against the slow, relentless drift of entropy. Cosmic rays, thermal noise, and hardware imperfections flip bits at random, altering ones into zeros and zeros into ones. Error-correcting codes, parity checks, and checksums quietly detect and fix most of these changes. The remaining faults become part of the background, occasional corrupted frames, damaged files, or unreadable sectors that system administrators accept as a cost of doing business at planetary scale. Against this backdrop, there is nothing special about the data associated with Atlas at first. Observations from telescopes, magnetometers, and spacecraft arrive as streams of packets and frames which are written to disks and tape libraries alongside countless other projects. Each dataset carries metadata that records when and where it was taken. Many archives also attach tags that indicate which object in the sky the measurements concern. Over time, an Atlas tag becomes one more label in a dense forest of identifiers that describe everything from nearby asteroids to distant clusters of galaxies. It is only when archivists begin routine health checks across large collections that a subtle deviation emerges. Automated jobs scan petabytes of stored information, reading blocks back and comparing them against stored checksums, the compact signatures that confirm whether the data remains intact. Most projects show a familiar pattern. A small but steady fraction of files accumulate correctable errors. A smaller fraction suffer permanent damage as disks wear out or tapes age. The pattern is consistent across file systems and facilities, varying mainly according to hardware type and environmental conditions. Within this general behavior, the Atlas tag datasets stand apart. Their error rates are lower than expected, sometimes dramatically so. Files that should by chance alone have accumulated a certain number of bit flips remain pristine. When the checksums are recomputed, they match the originals with unusual consistency. In some archives, entire directories containing months of Atlas observations show no errors at all, even though neighboring directories written in the same period using the same hardware display the usual mix of minor faults and repairs. At first, this is dismissed as a sampling artifact. Perhaps the Atlas datasets are newer or stored on higher-grade media reserved for high-priority projects. Archivists check for such biases, listing the ages of the files, the models of the drives on which they reside, and the environmental histories of the racks that house them. The differences are not large enough to explain the effect. In many cases, Atlas observations share devices with unrelated projects and yet show disproportionate stability. Teams explore the possibility that the Atlas files simply receive more frequent attention. High-profile projects often undergo more backups and verifications, which can catch and correct errors early. Log reviews, however, reveal that the maintenance cycles applied to Atlas are not significantly different from those used for other contemporary datasets. If anything, the surge of observations has made it harder to devote special attention to any one project. The improved integrity appears not to come from extra care, but from something inherent in the stored patterns themselves or in the conditions under which they were written. Statisticians are asked to quantify the anomaly. They model expected error distributions using known bit flip rates, storage ages, and usage patterns. Then they compare those distributions with the actual counts for Atlas-tagged files. The result is not an absolute absence of faults, but a pronounced deficit. Where the models predict a certain number of corrupt blocks, only a fraction appears. The deviation is large enough that repeated random trials almost never reproduce it. Over the combined holdings of multiple institutions, the chance that Atlas data would simply be lucky in this way shrinks to a level that calls for explanation. Attention then turns to the broader history of system events. Were there periods of unusually low radiation exposure during the times when Atlas data were written? Did the solar wind enter a quiet phase that might have reduced the rain of energetic particles through the atmosphere? Some intervals do coincide with calmer space weather, but others do not. Moreover, the same conditions would have benefited all stored data, not only the files tagged with the interstellar visitor's name. A more subtle pattern begins to appear when analysts align error log storage write times and the predicted trajectory of Atlas. The periods when its observations are recorded most intensively correspond to intervals when the synchronization event has already improved the coherence of global timekeeping and when the magnetometer arrays show their faint coordinated ripples. During these same intervals, the rate of uncorrectable errors in new Atlas-tagged files drops farther below expectation than in other projects created at the same time. It is as if the environment in which these particular bits are written and maintained is gently more ordered. This impression deepens when archivists examine older Atlas data written before the synchronization event and compare them with later data produced under the more coherent time standard. The earlier files show slightly higher error rates closer to what models predict. The later files show significantly fewer. The difference is not absolute, but it follows the evolution of the broader Atlas condition. Timing alignment improves, magnetic coherence emerges, simultaneous light anomalies proliferate, and within that emergent structure, digital patterns associated with the visitor grow more resistant to corruption. Technically, there is no clear path from the passage of an interstellar object through the inner system to the resilience of particular files on spinning disks and tape. Yet the correlations persist even under conservative analysis. One can imagine that the changed field conditions influencing Atlas might also influence the propagation of charged particles through the near-space environment, subtly altering how often they strike storage devices. One can also imagine that improved synchronization in the timing networks might lead to more efficient error detection and correction across the infrastructure. Both possibilities spread the influence widely, however, and do not readily account for why Atlas tagged data benefit disproportionately. In the absence of a definitive mechanism, practitioners adopt a descriptive phrase data that refuses to corrupt. It is not literally true. Atlas files are not perfectly immune to faults. But the phrase captures the tendency of these datasets to remain intact beyond expectation, as though they are carried within a quieter envelope of probability. In this way, the Atlas condition extends beyond light and fields into the digital foundations of observation themselves. The visitor is present not only in the sky and in the planet's magnetic response, but also in the patterns of ones and zeros that record its passage. Within those patterns, entropy seems for a time to lose a little of its usual reach. In the months after perihelion, as Atlas climbs away from the inner star, the work of reconstruction begins in earnest. The frantic pace of nightly tracking slows, and attention shifts from acquiring new measurements to knitting existing ones into the most precise possible account of the visitor's path. Celestial mechanics groups around the world assemble the complete archive of positions, velocities, and timing information, drawing from ground-based telescopes, space observatories, and deep space tracking stations. Their task is simple in statement and intricate in execution, to fit a single self-consistent orbit through the entire history of the object's journey through the heliosphere. At first, the process proceeds as it has for countless other bodies. Analysts adopt a standard solar system model with planetary masses and the mass of the star fixed to values that have been refined over decades. They include the contributions of radiation pressure and non-gravitational forces derived from outgassing. Sophisticated integrators trace trial paths forward and backward in time, adjusting initial conditions until predicted positions match observed ones as closely as possible. With so many high-quality observations, the expectation is that the final solution will be tightly pinned, leaving only very small residuals to be explained by noise. Yet when the dust settles, the residuals remain larger than anticipated. They are not chaotic, they show structure. In particular, they cluster in certain segments of the orbit, most notably during periods when Atlas threads regions of strong heliospheric field curvature and when the synchronized timing and magnetic anomalies are most pronounced. No combination of standard non-gravitational parameters fully removes these deviations. Increasing the strength of outgassing forces in the models overshoots the corrections in some intervals and worsens the fit in others. Adjusting the assumed orientation of the jets helps locally, but fails to produce a global solution that satisfies all epochs. A different line of inquiry emerges when one group treats the gravitational parameters themselves as variables. Instead of holding the mass of the star fixed, they allow it to vary slightly within the narrow bounds permitted by helioseismology and planetary dynamics. Similarly, they permit small adjustments to the gravitational parameter associated with the planet whose observatories contributed most of the tracking data. In principle, these parameters are known very well. In practice, every measurement offers a chance to refine them further, especially when it samples new regions of space and new combinations of distances and angles. To the surprise of those involved, the best-fitting solutions for Atlas's path consistently prefer a value for the solar gravitational parameter that is marginally different from the accepted standard. The difference is small, well within the formal uncertainties, and would not by itself justify a revision of any textbook. Yet its presence is persistent. Repeated fits using different subsets of the data and different integration schemes all converge on essentially the same, slightly altered value. When this value is applied, the residuals along the visitor's path shrink noticeably, especially in those segments where earlier models struggled. On its own, this would not be remarkable. Any single object can by chance favor a particular point within the accepted uncertainty range. What draws attention is what happens when the same adjusted gravitational parameter is applied to other independent datasets. When the revised value is used to reconstruct the orbits of planets and long-monitored asteroids over the same interval, the fits degrade slightly. Their residuals grow. The alteration that eases the path of Atlas disturbs the paths of bodies that have long served as anchors for the solar system's mass distribution. It is as though the visitor has passed through a slightly different gravitational environment than the one experienced by the rest of the system. Some investigators attempt to resolve this by introducing local perturbations rather than global changes. They treat the effective gravitational field as varying slightly in both space and time, adjusting it only in the regions where Atlas traveled and only during the months of its passage. In these models, the field returns to its conventional form before and after the event. With this flexibility, the fits improve significantly. The visitor's trajectory aligns well with observations, and the orbits of other bodies remain consistent with their long-term histories. The price is conceptual. Such models imply that for a limited interval, the gravitational environment behaved as if it were not entirely uniform. A parallel thread of analysis explores an alternate explanation. Rather than changing the properties of the star, these researchers modify the ephemeris of the observing planet itself during the critical intervals. By allowing the planet's own orbit to deviate slightly from its nominal path, they test whether a small positional bias in the reference frame could produce the same effect. To their surprise, a family of solutions emerges in which a tiny time-limited adjustment to the planet's position and velocity reconciles the Atlas data without altering the solar mass. When this correction is extended to other contemporaneous observations, some fits improve, especially those taken by instruments that share the same timing and magnetospheric anomalies noted earlier. Viewed in this way, the orbital paradox changes shape. Rather than suggesting that Atlas has revealed a different star, it suggests that the shared frame within which observations are interpreted may have been subtly shifted during its passage. The planet, its field, its clocks, and its data infrastructures may have participated in a temporary configuration that altered how distances and times combined into inferred positions. The visitor becomes less an object measured against a fixed background and more a participant in a joint arrangement that slightly redefines the background itself. The idea is not that gravity itself changed in any fundamental way, but that the effective coordinates used to describe it experienced a gentle system-wide modulation. Within this modulation, light traveled the same speed, planets followed the same laws, and instruments obeyed the same physics. Yet the net result, when reconstructed later under the assumption of a perfectly static frame, is that one body appears to require a different mass for the central star or a different orbit for the observing planet to make sense of its path. In internal discussions, this leads to cautious language. The orbital paradox is framed as an ambiguity between interpretations. Either Atlas has sampled a region where the effective gravitational parameter differs slightly from standard values, or the combined state of the observing system has imposed a subtle bias on the reconstruction. In either case, the phenomenon is tightly localized in time and space, coinciding with periods when other aspects of the Atlas condition are strongest. There is no call to revise fundamental constants, only an awareness that the passage of this fast interstellar fragment has revealed small flexibilities in the way the solar system's dynamics are inferred from finite embedded measurements. For most practical purposes, the paradox changes little. Spacecraft navigate successfully. Planetary ephemerides remain accurate for missions, eclipses, and tides. The adjustments involved are far below the threshold of daily experience. Yet for those working at the limits of measurement, the episode leaves a lingering sense that the act of observing is not entirely separable from the structures that make observation possible. Atlas has traced a path that sits at the intersection of gravity field geometry, timing infrastructure, and data integrity. In trying to fit that path into a single static picture, the system has revealed its own capacity to adopt briefly a slightly different configuration in which the usual constants appear under A over time. As the last clear images of Atlas's nucleus fade into the archives, the patterns that surrounded its passage become more prominent than the object itself. The precise point of light, the expanding coma, the changing tail, all of these have left their marks in observational logs. But it is the coordinated anomalies in timing, magnetism, and data integrity that continue to draw attention in meeting rooms and long technical reports. Gradually, the focus tilts from the material visitor to the state of the system that formed around it. In several institutions, working groups convene to review the full tapestry of effects. They gather specialists in celestial mechanics, space plasma, physics, timekeeping, digital archiving, and systems engineering. Each brings a different fragment of the story: simultaneous light anomalies seen across independent telescopes, microsecond adjustments in clock networks that improved global coherence, faint coordinated ripples in magnetometer arrays, storage logs showing uniquely stable Atlas-tagged data, and the orbital paradox that hints at a temporary gentle reconfiguration of the effective reference frame. At first, these elements sit side by side as separate curiosities. Teams present their findings, explain their methods, and offer cautious interpretations. No one suggests that a single mechanism must unify them. The world is large and coincidences occur. Yet as discussions continue, a shared vocabulary begins to form. People talk less about the comet-like object and more about the conditions that obtain during its passage. The phrase Atlas condition arises, informally used not to name the visitor itself, but to describe a recurrent pattern that appears wherever the object's trajectory intersects the systems that measure and remember. Under this emerging concept, Atlas is understood as the seed of a distributed state. The nucleus, the coma, and the tail play their roles as physical sources of light, heat, and plasma. But the condition extends beyond them into the surrounding heliospheric medium, into the planet's magnetosphere, and into the infrastructures that convert local measurements into shared knowledge. In this view, the visitor functions less as an isolated body and more as a moving node around which the environment temporarily reorganizes. The reorganization is subtle. Nothing overturns the laws that govern fields and particles. Rather, existing processes appear to operate in a slightly more coordinated manner. Timing networks designed to converge on a common standard do so with unusual synchrony when Atlas occupies certain regions of space. Magnetic field lines always in motion rearrange themselves with a coherence that crosses continents and orbits during key phases of the visitor's path. Error correction systems built to resist random faults succeed with atypical efficiency when working on data associated with the interstellar fragment. Each subsystem behaves within its design, yet collectively they realize a state that is statistically rare. To make sense of this without invoking hidden agencies, some analysts adopt the language of operating conditions. In large complex machines, different internal configurations can emerge depending on loads, inputs, and feedbacks. These configurations are not separate machines, they are modes that the same machine can occupy. By analogy, the combined heliospheric, magnetospheric, and informational environment may have modes of its own. One of those modes, triggered or at least shaped by the presence and motion of Atlas, is what the working groups begin to call the Atlas condition. In this mode, certain tendencies become more likely. Independent clocks slip into closer agreement with less corrective effort. Magnetometer stations record ripples that align more cleanly with upstream field structures. Light curves from distributed observatories show synchronized anomalies that are easier to reconcile when expressed in the shared temporal frame. Digital storage systems quietly preserve particular patterns of bits with lower error rates than statistical models suggest. None of these shifts is absolute. They do not create perfection, only a mild bias toward coherence. The idea that a moving fragment of matter could help steer a planetary scale system into such a mode is not framed as intention. There is no evidence that Atlas acts with purpose. Instead, the suggestion is that its passage through the structured fields of the heliosphere creates boundary conditions that for a time favor particular configurations of the environment. Its high speed, its unusual coupling to magnetic structures, and its richly observed trajectory make it a uniquely effective probe. As it moves, it illuminates the fabric it traverses, and the planet's instruments and infrastructures respond by shifting into patterns that reveal that fabric more clearly. Evidence for this remains circumstantial but layered. When the visitor is far from the inner system, the anomalies fade. Timing networks return to their baseline behavior of incremental, uncoordinated correction. Magnetometer arrays still register storms and quiet days, but the faint synchronized ripples tied so closely to the current sheet crossings diminish. Newly written data revert to ordinary error statistics. The orbital fits for other objects no longer favor localized adjustments to the effective gravitational parameter or to the planet's ephemeris. The Atlas condition relaxes, leaving behind only its imprint in the records. That imprint, however, is complex. It resides in synchronized timestamps, in residual plots, in error logs, in thermal and spectral maps, and in the long chains of corrections applied to clocks and orbits. When taken together, these records describe a distinct phase in the planet's relationship with its environment, a phase marked by heightened alignment between disparate systems. In this sense, the condition has migrated from matter into memory. The visitor's physical presence was temporary, but the pattern it helped bring into focus persists in the structure of the data. Some theoretical work explores whether similar conditions might have occurred in the past, unrecognized because no interstellar object of comparable speed and brightness happened to be tracked with modern instruments. Archive searches for correlated anomalies around other comets and asteroids reveal hints, but nothing is clear. Perhaps the Atlas condition is not unique, but has until now lacked a suitable tracer. Or perhaps the specific combination of its trajectory composition and timing with the solar cycle produced a rare alignment. The distinction remains open. Within the working groups, a gentle shift takes place in how the story is told. Atlas is no longer only a fast, bright visitor that passed through the inner system once and left. It is also the name of a particular arrangement of fields, flows, clocks, and memories that briefly cohered around that passage. The condition cannot be pointed to in the sky. It exists instead in relationships between instruments and their references between the planet's field and the heliospheric current sheet between stored bits and the processes that maintain them. In quiet terms, the conclusion that emerges is simple. A piece of interstellar matter arrived, was measured, and moved on. In the act of measuring it, the planetary system revealed that its own state is not monolithic. Under certain configurations, it slips into modes where coherence increases across multiple levels at once. Atlas served as both catalyst and indicator of one such mode. The object itself may one day be far beyond the reach of telescopes, its nucleus dark and quiet, but the condition that bears its name has become a reference point for understanding how matter field and information can briefly coexist in a more ordered pattern than chance alone would suggest. Long after Atlas has passed perihelion and climbed outward along its hyperbolic arc, the observing programs reach a practical limit. The nucleus dims as its activity recedes. The coma thins, the tail contracts, and the once vivid structure becomes a faint smudge barely distinguishable from the background star field. Telescopes that once captured detailed images now struggle to record anything above noise. Exposure times lengthen. Data pipelines strain to extract a signal. Eventually, many observatories concede that the object has fallen below their detection thresholds. Requests for further imaging time diminish, and the visitor begins to disappear from nightly schedules. Yet the ephemerides do not vanish. Predictive tables still list the expected positions of Atlas on future dates, tracing its path outward through the planetary region and beyond. Orbit integrators continue to project its trajectory into the dark, where, in the absence of new perturbations, it will drift forever in interstellar space. These projections become entries in long-term catalogs quietly maintained by institutions that track small bodies of all kinds, whether or not they remain observable. In equations and tables, Atlas persists as a set of numbers that connect the inner system to the wider galaxy. Around the same time, something curious happens in the infrastructures that once followed the visitor directly. Even after telescopes cease to return clear detections, timing networks, magnetometer arrays, and storage systems continue to show signatures tied to the predicted transits of the object. When the computed path carries Atlas through regions of strong heliospheric field structure, the faint coordinated ripples in the planetary magnetic field reappear, though slightly weaker than before. When the orbit model places the visitor in particular geometries with respect to the star, and the planet's micro-adjustments in clock alignment become marginally more frequent. These effects no longer carry the intensity they once did, but their pattern remains recognizable. Observers test whether these residual signatures might be driven by other causes that happen to coincide with the old trajectory. They check solar wind records looking for recurring structures that might impose their own rhythms on the field and timing systems. Some correlations exist, but they do not map cleanly onto the continued alignment with the predicted Atlas path. The simplest description is that the system behaves as if the visitor were still present in a diluted form, as though its transit has left a trace in the way the environment responds to certain configurations. In the digital archives, the trend in data integrity continues, though with a gentler contrast. Files written during later intervals when Atlas is predicted to be far from the inner system, but still within the broader heliosphere, show slightly lower error rates when they are tagged with the object's name. The difference is no longer as stark as it was near perihelion, but it remains measurable. It is as if the Atlas condition, once concentrated around the bright active phase of the visitor's journey, has expanded and thinned, leaving behind a dispersed echo that still influences how information settles into memory. This persistence is most evident when analysts examine long baselines. Over years, the pattern of simultaneous light anomalies gives way to something quieter, coordinated low-level fluctuations in background brightness that align approximately with the old trajectory when viewed from different vantage points. These fluctuations are not strong enough to claim as continued emissions from a physical object. They sit at the edge of instrumental sensitivity and might, considered in isolation, be dismissed as noise. But their timing when overlaid on the predicted path suggests that the geometry of the original transit still shapes how the system samples the sky. The notion of disappearance thus becomes more complicated. In a narrow sense, Atlas has vanished from direct sight. No telescope can reliably distinguish its nucleus from the dark around it. In a broader sense, however, the path remains active. Computational models, timing alignments, magnetic responses, and data integrity patterns all continue to refer in their own ways to the same moving coordinate. The object has become less a visible body and more a set of relationships carried forward by equations and infrastructures that were tuned in its presence. In practical terms, this means that the Atlas condition no longer requires the visitor to be easily seen. The condition has decoupled from the immediate brightness of the nucleus and integrated itself into the ongoing operation of the planetary system's measuring apparatus. The predicted positions in the ephemeris function like moving focal points around which subtle coherences gather. When those computed positions carry Atlas beyond the heliosphere and into interstellar space, the signatures finally fade almost to invisibility. Even then, small statistical deviations can be teased from the records as though the system remembers the path long after the traveler has gone. The phrase disappearance in plane computation is adopted in internal discussions to capture this transition. Atlas has disappeared from direct observation, but remains embedded in the computational frameworks that track it, and through those frameworks it continues to modulate the behavior of clocks, fields, and storage in a diluted fashion. The path has become an abstract object existing primarily in numbers and algorithms, yet still capable of shaping very slightly the way those numbers and algorithms behave. In this late phase, the visitor is almost entirely a construct of models. No new photons, ions, or thermal maps arrive that can be unambiguously tied to its physical presence. What remains are ephemerides, residuals, error statistics, and the intertwined histories of networks that adjusted themselves while the object passed through their domain. The Atlas condition has shifted from a response to matter into a pattern that lives primarily in the structure of ongoing computation. The visitor's absence, paradoxically, is what reveals how deeply its passage has been woven into the planet's distributed systems of understanding. Years pass and Atlas becomes part of the background in a new way. Its trajectory, once a focus of nightly updates and refined calculations, now appears as a stable entry in long-term catalogs. Students of celestial mechanics learn its parameters alongside those of earlier interstellar visitors. For many, it is a clean example of a hyperbolic passage, a curve that enters the heliosphere from afar and leaves again without return. The dramatic brightness, peaks, the complex tale, and the rapid motion are all preserved in textbooks and archives, yet they belong increasingly to a completed story. The systems that once registered the Atlas condition, however, continue to operate. Timekeeping centers still manage global clock networks. Magnetometer arrays still listen to the planetary field. Storage infrastructures still preserve observations, logs, and models. As new projects arise and old ones conclude, the vast body of data grows. Within it, subtle patterns accumulate that would not have been visible over shorter spans. Analysts who specialize in long-term trends begin to notice that certain correlations persist in the background, tracing shapes that resemble the old path of the interstellar visitor. One such pattern appears in long baseline studies of timing stability. When researchers examine the performance of the global time grid over many years, they find that certain intervals align unusually well with historical configurations of the heliospheric field. During these intervals, the clock network behaves as though it has slipped into a more coherent mode, requiring fewer corrections and showing tighter agreement between independent centers. The strongest of these episodes coincide with solar cycles and known phenomena, yet a subset of them appear along arcs in phase space that match where Atlas once traveled, as if the memory of its passage still informs how the system settles into order under similar field configurations. Another pattern emerges in analyses of the planetary magnetic field. Long sequences of magnetometer data compressed into spectral profiles and correlation matrices show faint enhancements along specific combinations of frequencies and spatial separations. These enhancements cannot be traced to recurring storms or to familiar solar drivers. Instead, they draw a curve through the data space that closely follows the projections of the orbit solution for Atlas extended and generalized to other epochs. Wherever the planet's position relative to the heliospheric current sheet echoes the geometry of the visitor's passage, the field exhibits a slightly higher tendency toward the same kind of gentle system-wide ripples observed during the original event. In digital archives, the residual resonance takes the form of uneven error statistics. While overall storage reliability improves with advancing technology, the patterns of which data sets prove most durable remain uneven. Projects that sample the sky along certain lines of sight or that record field measurements under specific configurations of solar and planetary geometry show marginally lower rates of corruption and loss. When these configurations are mapped into heliocentric coordinates, they cluster around the families of trajectories that resemble the old Atlas path, as though the condition first established during its passage has left a template that still influences how information settles into memory when similar geometries recur. These resonances are small and would be easily lost in noise were it not for the vast volume of data now available. It is only by examining many years of records that their shapes emerge. Even then, they remain statistical tendencies rather than absolute rules. There are intervals when the geometry matches, and yet no particular coherence arises, and others when coherence appears without obvious relation to the old trajectory. The memory is imperfect, like a pattern in sand that persists under repeated waves, but never in exactly the same form. Conceptually, this leads to the idea of a field-level memory. Not memory in the sense of a stored image or a discrete record, but memory as a bias in how systems respond to certain configurations. The heliosphere, the magnetosphere, and the informational infrastructures built within them seem to retain a faint preference for the state they once occupied when Atlas passed through. When configurations of field and position approximate that state, the systems show a slightly higher propensity to fall into similar modes of coherence. When configurations differ strongly, the bias fades into the background. In this way, the Atlas condition becomes less an event anchored to a single object and more a mode that the combined environment can access. The original passage served as a kind of training episode during which the system explored a particular configuration of timing, magnetism, and data flow. Once that configuration had been realized, echoes of it became easier to reach again when circumstances aligned. Over years, this yields residual resonance, not a direct continuation of the original state, but a series of gentle returns toward it scattered through time whenever geometry and field structure fall into compatible arrangements. The idea does not imply agency or design. No intention is assigned to the system. Instead, the resonance is described in the language of dynamical systems and attractors. Complex networks often exhibit a tendency to revisit certain configurations once visited, especially when internal feedbacks and external drivers conspire to make those configurations stable. The Atlas condition in this framing is one such configuration, a shallow basin in the space of possible global states that the system occasionally re-enters. For those who study these phenomena, the practical implications are modest but intriguing. Understanding the residual resonance may improve models of timing stability, magnetospheric behavior, and data reliability under specific heliospheric conditions. It may also serve as a reminder that large coupled systems have histories that shape their future responses. The planet's relationship with its environment is not fully captured by instantaneous variables. It also depends in subtle ways on what configurations have been realized before. In public narratives, little of this appears. Atlas remains known primarily as a fast interstellar visitor that briefly lit the inner system. The deeper story of residual resonance and field-level memory circulates mostly in technical communities, where it joins other examples of how complex systems remember. For those who follow it closely, the lasting impression is one of quiet continuity. The object has gone, but its passage has left the planet and its measurements with a slightly different texture, a faint preference for coherence that resurfaces along old arcs whenever the sky and the fields fall into familiar patterns. With the immediate passage of Atlas now firmly in the past and its residual resonances woven into long records, reflection turns naturally toward what, if anything, the episode suggests about the broader nature of interstellar visitors. In conference halls and quiet offices, theorists and observers consider the possibility that Atlas was not simply an isolated fragment of matter but a manifestation of a more general process. The idea arises that what arrived in the inner system may best be understood not as an object alone, but as an object carrying with it the capacity to establish a particular condition. This line of thought begins with simple observations. Atlas behaved like a comet in many ways, with a nucleus coma and tail responding to sunlight and the heliospheric environment. It followed a gravitational path that can be described with familiar equations, modified only gently by non-gravitational forces. At the same time, its presence correlated with synchronized timing adjustments, thermal divergence, simultaneous light anomalies, magnetic coupling across large scales, and unusual stability in associated data. These are not traits of matter alone, they are traits of systems in which matter fields and information interact. One speculative view holds that certain interstellar bodies may be carriers of autonomous processes that extend beyond their physical boundaries. In this perspective, an object like Atlas does not merely pass through a system, it invites the system into a temporary mode of operation. The invitation is not conscious or directed, it arises from the way the object's plasma environment couples to magnetic fields, how its rapid motion samples gradients, and how the resulting signals propagate through networks of instruments and computation. When the conditions are right, these interactions can coax the planetary environment into a more coherent configuration, a condition that once established persists briefly and leaves behind a template in memory. Another view emphasizes the role of the observing infrastructure itself. Atlas in this framing served as a test input for a mature planetary sensing and information system. By tracking a fast, bright interstellar object through a complex heliospheric structure, the system revealed its own hidden modes. The Atlas condition could then be seen less as something imposed from outside and more as an emergent property of the interconnected instruments, clocks, and archives. The visitor provided the right combination of stimulus and geometry for those properties to surface. Between these views lies a shared recognition, whatever Atlas was in itself, it functioned as a catalyst for revealing a particular way in which the combined environment of star planet and technology can organize. Whether similar conditions arise in other systems depends on how their observers are distributed, how their fields are structured, and how their records are kept. An interstellar visitor of the same physical type might produce very different effects in a system without global timing networks, deep magnetometer coverage, or extensive digital storage. In such places, the same underlying process might remain invisible, its condition unrecognized. The question of intent is addressed gently and left unresolved. No evidence suggests that Atlas steered itself, altered its path deliberately, or responded in a directed way to the presence of instruments. Its behavior is consistent with known physics extended into complex regimes. Yet the idea persists that processes can appear purposeful at scales where feedbacks and couplings produce organized patterns. The Atlas condition fits into this category, a phenomenon that, while not necessarily designed, exhibits a degree of coordination that invites contemplation. Speculation stretches further into the possibility that a process might migrate from matter into field and memory. In this extended view, an interstellar visitor could arrive as a physical body, interact with local fields in ways that produce a distinctive operating condition, and then depart, leaving the condition partially encoded in the system's own records and tendencies. Over time, that condition might propagate not through new arrivals, but through the reuse of patterns in timing, magnetism, and data flow. In this sense, the visitor's most lasting presence would not be its physical remnants, but the way it changed the rules by which the system prefers to organize itself. These ideas remain firmly speculative. No experiment can yet distinguish conclusively between coincidence, emergent behavior, and some deeper organizing principle. The evidence is subtle, distributed across many kinds of data, and always open to alternative explanations. Still, the episode leaves those who study it with an expanded sense of what it means for a system to be visited. The arrival of matter from another region of the galaxy is no longer imagined only as an impact, a passage, or a source of samples. It is also imagined as an opportunity for the host system to explore different modes of coherence under the influence of a new pattern. In the end, the Atlas condition is described in restrained terms, a temporary planetary scale experiment conducted without design in which an interstellar fragment, a structured heliospheric field, and a mature observational infrastructure together created a state of heightened alignment. That state touched clocks, fields, light curves, orbits, and data storage. It faded, leaving behind faint resonances and a more detailed map of how the system can behave. What remains open is whether future visitors will evoke similar conditions, whether other stars host their own versions, and whether the quiet modes of coherence that arise under such influences play any broader role in the long story of matter moving between worlds. The sky returns to its usual patterns. The heliospheric current sheet continues to warp and rotate. Comets and asteroids follow their own paths, sometimes brightening, sometimes fragmenting. Instruments keep watching, not in expectation of a repeat, but with a slightly altered understanding of what their readings might contain. Somewhere beyond the reach of telescopes, Atlas travels on dark and unremarkable in appearance, while the condition that grew around it remains as a subtle, persistent possibility in the fields and memories it once gently rearranged.